linked list is a linear data structure where elements are connected to each other using pointers or links. In this illustration, the blue circles represent nodes of the list, the arrows represent pointers, and the yellow texts represent memory addresses of those nodes. Unlike arrays, where elements need to be stored in contiguous memory locations, elements of a linked list can be allocated anywhere in memory. This flexibility allows linked lists to efficiently utilize memory by allocating space as needed, making them more dynamic and adaptable to varying storage requirements. Each node in a linked list contains the data and a pointer or a reference to the next node. This reference is simply the memory address of the next node. The first node of the list is known as the head node, and the last node of the list is known as the tail node. This specific type of linked list is known as a singly linked list because there is only one pointer per node. We will explore other types of linked lists later in the video. Now let's see the implementation of the linked list and the operations on it, along with visual animations. We will use Python for this because it is an easy and beginner-friendly language. First, we will define a class called node. In the constructor, we will take data as input and initialize two members, data and the next pointer, which will be initially set to none. This structure allows us to create individual nodes that can be linked together to form our linked list. Then, we'll create the class linked list. In this class, we'll define the member variables head and tail to keep track of the first and last nodes of the list. After that, we'll define the other operations we need to manage our linked list, such as insertion and traversal. Let's first start with the traversal operation. We will define a function called traverse. Inside this function, we'll create a variable called current, initially set to the head node. We'll then run a loop with the condition while current is not none. In each iteration of the loop, we'll print the data of the current node and then move current one step forward by updating it to the next node. This loop will continue until current becomes none, indicating that we've reached the end of the list. And after the loop ends, it will simply print null to indicate the end of the linked list. Now let's remove these address labels to make more room on the screen. The next operation is searching for an element, which is quite similar to traversal. We'll start by defining the function with a key or target element as the input parameter. Inside the function, we'll create a variable called current, initially set to the head node. We'll run a loop with the condition while current is not none. In each iteration of the loop, we'll check if the data of the current node matches the target value. If it matches, we'll return true. If not, we'll update current to its next node and continue the loop. If the loop ends without finding the element, we'll return false. Now let's see this in animations. Let's say you want to search for the element containing the data 4. First, we'll create the current variable and start by checking its data. If the data doesn't match 4, the algorithm will move current one step forward and continue checking the next node. This process will continue until either the data matches 4 or we reach the end of the list. If we find the element, we return true. Otherwise, we return false once we have traversed the entire list. Both the traversal and search operations have linear order complexity because they both involve iterating through the list in a loop. The next operation is inserting an element at the beginning of the list. We will start by defining a function with the new data as the input parameter. Inside the function, we'll create a new node using this data. We then need to check if the head is none, which indicates whether the list is empty. If the list is empty, we'll assign both the head and tail to this new node. If the list is not empty, we'll set the next pointer of the new node to point to the current head node, and then update the head pointer to this new node. Inserting at the end is also similar. It starts with defining the function, with the new data as the input parameter. Next, it creates a new node with this data. The algorithm then checks if the list is empty. If it is, it assigns both the head and tail to this new node. If the list is not empty, it sets the next pointer of the current tail node to the new node, and then updates the tail to the new node. Both inserting at the beginning and at the end of a linked list are constant time operations because they involve only a few pointer changes. Next, we'll discuss inserting at a specific position in the list. First, we'll review the code and then look at a visual example. We'll start with defining the function, taking new data and index as input parameters. We first create the new node. The algorithm will then check if the index is 0. If it is, it will perform the insertion at the beginning operation as described earlier. If the index is not 0, we'll create a variable called current, initially set to the head node. A loop will run to traverse just before the index where the new element is to be inserted. If current becomes none while traversing, it will indicate an index out of bounds error because the desired position is beyond the end of the list. Otherwise, we update current to its next node. Once the loop ends, we update the next pointer of the new node to point to the next node of current, and then update the next pointer of current to point to the new node. Finally, we'll check if the new node is the last node. If it is, we update the tail pointer to the new node. Let's say you want to insert data at the third index. First, the algorithm will create a new node using the new data. Then, it will create a current variable starting at the head, and traverse until it reaches the node just before the target index. The algorithm will then adjust the pointers accordingly to insert the new node at the specified position. This operation takes linear time because the algorithm needs to traverse the list to reach the target index. Next is deleting from the beginning of the list. This operation will start with defining the function. The algorithm first checks if the list is empty. If it is, the function will simply return. If the list is not empty, it will check if the head and tail point to the same node, which would mean the list contains only one element. In this case, both head and tail will be set to none. If the list has more than one element, the algorithm will move the head pointer to the next element. Since we are using Python, we don't need to manually delete the first element because Python handles memory management automatically. However, in languages like C++, you would need to explicitly delete the node to free up memory. Next, let's discuss deleting a node from a specific position. We'll first look at the code and then the visuals. The process starts with defining the function, taking the index as an input parameter. The algorithm first checks if the list is empty. If it is, the function will simply return. If the index is 0, it will perform the delete from beginning operation as described earlier. If the index is not 0, the algorithm will create a current variable, initially set to the head node, and traverse the list up to the node just before the target index. After the loop ends, it will check if the current node is the tail. If it is, the tail pointer will be shifted to current. The algorithm will update the next pointer of the current node to skip the node to be deleted, pointing directly to the node after it. Since we are using Python, memory management will be handled automatically. Now let's say we want to delete the element at the third index. The algorithm will create the current variable and traverse the list until it reaches the node just before the target index. It will then update the next pointer of this current node to point to the node after the one to be deleted, effectively skipping the node at the third index. The next operation is reversing the entire list. We'll start by defining the function reverse. First, we create a variable called previous, initially set to none, and a variable called current, assigned to the head of the list. The tail will be updated to become the head. Then, while current is not none, assign next node to current.next to keep track of the next node. Then update current.next to point to previous, effectively reversing the link. Then update previous to current, and then move current to next node. The loop will continue until current becomes none. Once current becomes none, the loop will break. Finally, we will update the head to point to previous, which is now the new head of the reversed list. Reversing the entire list is a linear time operation because it involves traversing the list once. Before moving to the doubly linked list, let's summarize all the operations and their time complexities. Insertion at the beginning and end is a constant time operation because it only needs to change a couple of pointers. Inserting at a specific position takes linear time because it traverses the list up to the index. And deleting from the beginning takes constant time, while deleting from the end or any specified index takes linear time because of the traversal. And searching, traversing, and reversing all take linear time. And space complexity is constant in every operation because it does not need extra memory beyond a few pointers.